Hi, thanks for joining us today. I'm Shrikant Rana. I'm a solutions architect at Databricks. And today, Yusuf and I are going to talk about how you can build an end to end solution for regulatory grade multimodal data de-identification and tokenization using Databricks and John Snow Labs. For those of you who are new to Databricks, we are the data and AI company. We are the inventor of the Lakehouse and also creators of many successful open source projects like Apache Spark, MLflow, and Delta Lake. As the inventors of the Lakehouse platform and leaders in open source innovation, we are committed to shaping the future of data and AI. Our data intelligence platform is the realization of that vision. The platform is a unified AI powered solution built on top of Lakehouse architecture that combines the flexibility of data lakes and performance of data warehouses. It supports storing all types of data and supports diverse workloads like data ingestion, data engineering, BI, machine learning, and Gen AI, all on one single platform. With Unity Catalog, it delivers centralized governance, access control, and data lineage on all of the data and AI assets. The platform is infused with AI capabilities that has knowledge of the data and the metadata in the lakehouse, which helps in automating the data cataloging, optimizing performance, enabling natural language queries, making data easily discoverable and usable for everyone in the organization. So let's understand regulatory grade de identification in healthcare. It's the process of removing, masking, or transforming personally identifiable information or protected health information from datasets to meet strict legal and regulatory standards. The purpose here is to ensure that data cannot be traced back to a specific individual. It's also important to minimize any kind of like re-identification risk while preserving analytical value for research, analytic, and regulatory data submission purposes. But why does it matter? Well, it's required for regulations such as HIPAA, GDPR, and CCPA. Health systems and insurers that do not comply with these regulations attract legal penalties and reputational damage. De identification also helps with risk mitigation. It reduces the risk of data breaches, unauthorized disclosures, and regulatory penalties. Data de identification also acts as a data utility. It helps organizations use and share data for insights and innovation without exposing sensitive information. And finally, regulatory frameworks require documentation, justified risk assessments, and transparent de identification processes for auditing purposes. Now, let's see how Databricks enables secure and compliant de identification of sensitive information. It does that through a combination of compliance features, security best practices, and platform features. Let's look at them one by one. Databricks supports multiple compliance with several industry specific and international regulatory requirements such as HIPAA, GDPR, CCPA, PCI DSS. When it comes to security, Databricks has worked with thousands of customers in deploying Databricks data intelligence platform that meets the security, privacy, and regulatory requirements of the organization. While many organizations deploy security differently, there are patterns and features that are commonly used by most organizations. Here are the most relevant controls, that is, define security controls, deploy security controls, and monitor security controls. Let's look at them one by one. When it comes to defining security controls, our security best practices white paper provides a detailed checklist of the main and the most prevalent security controls we recommend for typical high-end security deployments. When it comes to deploying security controls, our security reference architecture Terraform template makes it easy to automatically provision Databricks environments that follow the security best practices. And finally, when it comes to monitoring the security controls, our security analysis tool continuously monitors the security posture of your Databricks data intelligence platform in accordance with these security best practices. Now let's look at some of the Databricks platform features. So system tables is one of the capability. It can be found in your system catalog. It provides historical observability of all the activity happening across your Databricks account. Tables such as audit logs, billable usage, query history, network access events, and many other data sources, they provide comprehensive audit logging that enables organizations to monitor user activity, detect anomalies, and support compliance reporting. Let us look at some de-identification techniques native to the Databricks platform. So Unity Catalog fine-grained access control is a native capability that allows you to implement row-level filters and column-level masking on tables to filter and protect sensitive data. You can also create dynamic views to protect sensitive data at query time. This option is specifically useful for more advanced SQL-based logic and complex SQL expressions that spans multiple tables. Databricks platform also has several de-identification techniques using built-in functions. For example, you can leverage regex underscore replace to implement anonymization of sensitive columns. Databricks also has built-in AES, the advanced encryption standard-based functions that converts data into unreadable ciphertext. This is especially useful if encryption and decryption are needed for data at rest, data in transit, and data in processing. Hash is a built-in function that converts data into irreversible deterministic hash values. This is helpful in scenarios when there is a need to perform data integrity checks. Mask is another built-in function that helps with partial or complete data concealment. It's helpful when there is a need to display data to authorized users in a user-friendly format. So far we have seen several techniques to implement de-identification of structured and semi-structured data. I'll now hand it over to Yusuf to cover multimodal data de-identification and tokenization using Databricks and John Snow Labs.
Thank you, Srikant. Hi, everyone. This is Youssef, Senior Data Scientist and PhD at Johnson Labs from the healthcare team. I'm happy to be with you today in order to present, in coordination with Srikant, of course, the Johnson Labs multimodal medical data identification and tokenization or obfuscation at scale using um, Databricks. But before starting, what is multimodal identification? So as you know, the multimodal identification is the process of removing patient identifiable information across all data type. So for example, for the same patient, we can have multi-type of documents, for example, clinical notes, tables, or structured data. You can have some DICOM images, SVS, or PDFs, either selectable or scanned PDFs for each patient. Okay, so the goal here is to ensure every modality is identified and all data for the same patient remains consistently linked. Okay, so the role here or the goal is to identify, and if we want to, let's say, uh, obfuscate, so we need to keep the consistency after the identification. But why multimodal identification matters? So as you know, healthcare data is heterogeneous. It means you can have multiple document type, for example, for text notes, structured tables, medical images, for example, DICOM, SVS, images. Also, we can have scanned docs like PDFs. And as you know, when we talk about identification and to be compliant with the rules like IPA and GDPR, we need to mask or identify PHI that can exist anywhere. Okay, uh, and the same regulatory compliance requires complete, consistent identification across modalities. And also, we need to keep the linkage between the the data or the obfuscated PHIs. So this will enable research and analytics on multi-source data without exposing patient identities. But how it works using Johnson Labs NLP pipeline and what is the solution stack. So here I designed the schema in which we present the how it works the Johnson Labs healthcare NLP pipeline in combination with visual NLP in order to cover the multimodal medical data identification at scale. So here we assume that for the same patient, uh, he has multiple input documents, for example, scanned PDF, DICOMs, clinical free text, structured data like CSV, and so on. So this is the input. So the first check is we need to check if the data or if the document type is visual. If it is visual, so here we need some of the OCR techniques that are included in the Johnson Labs Visual NLP in order to extract the data from the, let's say, the scanned images or, for example, scanned PDFs or, for example, from the DICOM pixels. So after that, we can just feed the text into the Spark and the healthcare NLP. Or if we have, let's say, free text, like clinical free text, uh, we can just feed the text into the Spark NLP healthcare or healthcare NLP pipeline to detect the PHIs, after that to identify the PHIs. So here we have a zoom at the bottom. As you can see, we have a zoom of the stages that we can build and customize regarding the Spark and healthcare NLP pipeline. So the first stage is almost the document assembler that takes the text. After that, we have the sentence detector that detects the sentences from the document. After that, we can add the tokenizer in order to tokenize the sentences detected. After that, we can add some of the components, for example, for the normalization of the text or of the tokens. And after that, we can convert the word into embedding, into vectors, then feed the vectors into the machine learning or deep learning models that are here, the NER models, to detect the PHIs. And also, in the same pipeline, we can have one or multiple NER models to detect PHIs. And also, we can reinforce the same pipeline with the rule-based approaches, like, say, contextual parser rules based on prefix, suffix. Also, we can add some regex matchers, also some contextual entity rulers, in order to reinforce the detection of some of the PHIs. After that, we can just merge all together in the same pipeline, then feed the output into the identification annotator responsible of the identification after detecting the PHIs. So we can just configure the identification component in order to identify the PHIs according to the business rules. For example, some of the entities we can configure to mask the patient name, doctor name, and we can configure to obfuscate the SSN, MRN, and skip some of the other entities and so on. So here it is fully flexible. Okay. And for this Spark and healthcare NLP pipeline, so we do have multiple protein pipelines that you can use out of the box. And also you can build your custom pipeline with your custom NER models. Also, we do have multiple NER models that can detect PHIs according to the rules. Also, you can train your custom NER model to have a strong pipeline tailored for your data for the identification purpose. Regarding the solution stack, so for the data sources, so here in this case, we can have multiple or any document type, for example, structured data, CSV, Parquet, relational databases. Also, we can have free clinical texts, PDF files, either scanned or text. Also, we can have DICOM images and so on. For the pre-processing or the processing, so here we will use Databricks, notebooks, and jobs. Also, we can use that Databricks runtime plus Spark Engine, also cluster management inside Databricks. For the GSL NLP suite, as I mentioned, it is a pipeline in which we can put multiple stages here, since we can have some visual document like scanned PDFs and images and DICOMs. In this case, we need to use visual NLP from GSL, then feed the output into the healthcare NLP pipeline. For the identification workflow, so it is the same. So if we have visual data, so we apply visual NLP, then feed the output into the NLP pipeline. Otherwise, if we have just textual data or structured data, we can just use the healthcare NLP pipeline to detect PHIs, then identify them according to the business rules. For the output or the storage, so we can store the output into DBFS, the Databricks file system in this case, or also we can store or save the native data into external storage. For the security and compliance, so we do have multiple models that are compliant with HIPAA rules, GDPR support. Also, we can make some audit, logs, access control, and so on. For the monitoring and quality, so in Databricks, we have the Databricks monitoring and logging. Can use Spark UI in order to monitor the quality and the resources. The application quality checks, we can check also the accuracy, the coverage, error analysis regarding what are the PHI that are well detected, how can we improve the accuracy, and so on. Now let's jump into an end-to-end GSL solutions demo on Databricks regarding uh, multimodal medical data identification and tokenization at scale. So here on Databricks, okay, as you can see here, we have some dependencies regarding the Johnson Labs libraries, Visual NLP, Spark NLP, and so on. Here I prepared two notebooks, one to show you how to establish the masking policy for the multimodal identification. And the second notebook, we have multimodal obfuscation at scale. So it means in first we will just mask the PHIs, and in the second we will obfuscate or tokenize the PHIs with faker data by keeping consistency. Okay. So here is the first notebook. Here the case study is that we assume that we have just one patient named Martin Chad with just one clinical note, one PDF, scanned PDF, one structured data, one DICOM file, okay? Just to, for the experimentation, to show you how to achieve the multimodal medical data identification and obfuscation. So here, so let me zoom in a little bit, just to see the code. So here, first thing that you need is to import the Johnson Labs library, NLP, visual, and medical. Okay, so let me run this cell. Okay, here we do have the NER healthcare NLP pipeline. So remember that in the slide here, as you can see, we have the Spark and healthcare NLP components in which we need to feed the text to establish the identification. Okay, so it is the same component. Either we have uh, the free text or visual NLP text. So we need this Spark and healthcare NLP components or pipeline that is based on, let's say, NER models to detect PHIs. Okay, and it is fully flexible. You can build your own pipeline with your own stages, and also you can just use your own, train your own in your model and put it in the same pipeline, or use multiple models with multiple regex and rule-based approaches to reinforce the pipeline to detect well the wall, let's say, PHIs that you have in your data. So here, as you can see, we have this function in which we built a simple pipeline with document assembler, tokenizer, and here, as you can see, I'm not using the sentence detector because here I'm using the docwise model, the NER model, which is based on the Word document, not just sentences, in order to reinforce or in order to give the NER model more, let's say, more context to well detect PHIs. Okay, so here we have document assembler, tokenizer, word embedding. Here we have the NER model, okay, coming from the medical library from Johnson Labs. And of course, here we have the NER converter in order to convert the token into chunk-based detection. And here, as you can see, we are whitelisting some of the entities. For example, here we are interested into detecting and masking just the names, dates, age, and ID, okay? And you can play with this parameter. And also we have set blacklist to block list the entities that you don't want to identify and so on. So we do have multiple parameters that you can play with in this annotator. I invite you to check the Johnson Lab documentation for more details regarding each component, how it works, and what are the parameters that you can play with. Okay, so here we are putting it all together. So the wall stages, as you can see, one after one. So we have document assembler, tokenizer, embedding, clinical NER, then the near converter, and so let me just execute this part. Then here we have the first modality or document type, which is unstructured data. Okay, so here we do have the identification annotator. Okay, in which you can configure your business rules or how you want to identify your PHIs detected by the NER models. Okay, so here, for example, I'm using multiple identification annotators or components, each one using one mode. So here we have set mode, so the masking mode, because as I mentioned, this notebook is just for masking the PHIs. Okay, so here in the using the identification annotator, you can use the policy masking with entity labels, or masking with the same length chart, or masking with fixed length charts. Okay, so here masking with entity labels means for each PHI detected, it will be replaced with its label. For example, if we have a name well detected, so it will be replaced with the tag or the label name. Okay, here in the identification pipeline, so here we are calling the same function here from the coming from the NER healthcare NLP pipeline. This is the function in which it contains just NER model to detect PHIs, and here we are configuring the identification, how to identify those PHIs detected by the NER pipeline. So here we are calling our healthcare NER pipeline, and we are adding just those stages, okay, regarding the identification. Here we have a new pipeline regarding the identification. Okay, so it is downloading the models. So here we have some of the models, NER models downloaded from the Models Hub. And here we are just fitting the pipeline to have the pipeline model. And here we have a simple text, okay? So it is a figure text. Regarding the patient Martin chart, we have patient name Martin chart, we have date of birth, we have some of the history, medical history. Here we have the age, here we have the same name, and so on. Okay, so let's apply the model identification pipeline and see the results, the outputs. So as you can see here, we have the initial document. Okay, we have the initial text, and here we have the identified text with entity label. Okay, so Martin chart, it is identified with the name, date of birth with dates. Here again we have Martin chart. Okay, the name Martin chart, so it is well detected and identified with entity label name. And here we have the age. As you can see, it is well detected and identified with age label. Okay, here we do have the two other policies regarding the masking. So here we have masking with same length chart, so it means the same length that we have in the name, so it will be replaced here with asterisks. And here we have identification with fixed length. Remember here in the identification, in the third identification with the masking policy fixed length chart, here we are adding the set fixed mask length 4. This is why we have the identified results with just 4 asterisks, okay, for the wall PHIs. So this is a simple experimentation regarding how to mask the unstructured text, free text. Okay, so let's see the results regarding structured data. Okay, for the same patient, which is Martin chart. So here we assume that we have some CSV, or let's say Excel file, or in general structured data. As you can see here, for the same patient, here we have multiple patients, one row per patient. Okay, so here the first row, so we have some of the information regarding the same patient, which is Martin chart. Patient name, date of birth, it is the same date of birth. We have the age and some of the other information, and here we have other patients. Okay, we are interested in the same patient, which is Martin chart. So this is the input. So let me see the output regarding the masking. Okay, so as you can see here, for the patient name, the whole patient name are masked with asterisks and the date of birth and age. Okay, so we can configure here what are the PHIs or the columns to be, of course, to be masked. Okay, and the third modality is PDF data masking. So let's see how it works the PDF. So again, we will use in the final pipeline, as you can see here, we are calling the Duncation NLP pipeline, the first pipeline, in which we have the NER models to detect the PHIs. It is the same NLP, or it is the same healthcare NLP pipeline to detect the PHIs used here, and this pipeline for PDF. Okay, so as you can see here, we have some pre-stages in order to, as I said, and remember here. So let me come back here to this schema. As you can see here, if we have some OCR needed, in this case, we have PDF, scanned PDF. So we need some OCR to extract the data from the scanned PDF. So here we need to call some of the visual NLP from Johnson Labs library to extract the data, then feed the data into the same pipeline. Okay, so those are the stages that we added regarding PDF pre-processing. Okay, PDF to image, image to text. So here we have image to text and image to HOCR in order to get the text from the image. Okay, and here we have position finder in order to find some of the positions of the PHIs in the scanned PDFs, giving the output coming from the PHIs. Okay, here we have image draw region in order to draw the black box in order to mask the PHIs in the scanned PDFs. Okay, so let me run again uh, this PDF pipeline. Okay, okay, good. So here, so let's load and see uh, the Martin chart PDF. So let me display it here to see the input, how it looks like. So it is a PDF. So it is clinical note Martin chart PDF. So as you can see here, we have the scanned PDF. Okay. So patient name, date of birth. We have some of the medical history for the same patient here. We have some of the texts, and at the end we have some the same date of birth and patient name. Okay, let's see now, after applying the identification pipeline, PDF identification pipeline on our PDF, let's see side by side output comparison between the inputs and the outputs. Okay, so here, as you can see, this is in the left, this is the original PDF, and this is the masked PDF. Okay, so as you can see here, we have the patient name well masked, the date of birth, the patient name, the age. Again, here we have patient name Martin Chat. Okay, so it is well masked, and also we have date of birth well masked, and the Martin Chat patient name is well detected and well masked. Okay, let's see how it works with the DICOM data masking. Okay, so here again, since it is a pixel or visual document based document, so we need to add some of the components again in the final pipeline, then feed the output into our same healthcare NLP pipeline to detect the PHIs, then identify the PHIs in the DICOM image. So here we have some of the DICOM related pre-processing parts, visual using visual NLP to extract the information from the DICOM, because in the DICOM we can have metadata and some of the pixels, some of the images. Okay, so here we have the components, DICOM to image, image text detector from the DICOM. Then here we have some other components, and then we have the position finder to find the positions of the PHIs in the DICOM, and putting it all together into the same identification pipeline. Okay, so let me run it again, this one, and let me show you. So okay, so let me show you. So I'm loading Martin chat on DICOM. related to Martin chat. So as you can see here, we have some of the metadata, and here we have the let's say the DICOM image or the pixel of the DICOM. So as you can see here, we have some of the radiology, some of the DICOM regarding Martin chart, and some of the information. So here we have PHI. As you can see, we have the patient name. So we have Martin chart and the date of birth. So it is the same date of birth of Martin chart. Okay. So this is the DICOM, the input DICOM. Also, we have some of the same PHI here in the metadata. So patient name, as you can see here, we have Martin chart. Okay. And yeah, this is the patient name in the metadata. So this is the input. So let's apply the the DICOM identification pipeline to see the output of the identified DICOM. So it's running. So let's see the output. So sometimes it takes a little bit time. It depends on the resources that we have actually. But let's see. So this is the multimodal masking using Johnson Labs capabilities running on Databricks. So let's wait for this, and we will come back to the output regarding masking the DICOM. So let's see the other notebook regarding the obfuscation, multimodal obfuscation. So here I will not run. So we because we have the output for each cell. I hope, yeah, we have the output. So let's see just directly the output. Okay, see if we have, okay, so here, so it is done. So multimodal masking for the DICOM. So as you can see here, we have the DICOM uh, patient name and the date well masked. Okay, so let's come back to the obfuscation, multimodal obfuscation for the same patient, which is Martin chat. So here for the obfuscation or tokenization, so the purpose is to replace the PHIs with faker data and keeping consistency. Okay, here again we have the same healthcare in-year healthcare NLP pipeline in which we have document assembler, sentence detector, tokenizer, word embedding, and we have the in-year model. Okay, you can play with in-year models that we have. We have a lot of pretend in-year models in the models hub. Okay, I will share with you the links at the end of the presentation regarding the models hub in which we have multiple GSL out-of-the-box pretend models that you can put here according to your needs. Okay, also, we do have multiple pertinent pipelines that you can run with one liner of code to redact or to identify your nodes. Or if you want to build your custom pipeline, also if you want to train your custom in-year model and put it in the same pipeline, so it is fully flexible. So here, as you can see, we have the same NER pipeline. So let's go to the unstructured data obfuscation. Okay, unstructured data obfuscation. So it is the same input text for the unstructured text. Okay. Here we have Martin chat and the date of birth. Here we have the age, Martin chat again. So let's see the outputs. Okay. After applying, of course, after applying the obfuscation model coming from the obfuscation pipeline. Okay. So this is our obfuscation pipeline. Here again, after building the healthcare NER pipeline, so we need to add the last stage, which is the identification. As I said, the identification annotator, which is this one coming from the medical identification, in which you can configure how to either mask or obfuscate your data. And we do have a lot of parameters that you can play with in the identification to configure how to obfuscate or how to mask your data. So here we are using set mode obfuscate instead of masking. Remember, before in the masking, we set mode masking and we set the policy. Here we set mode obfuscate in order to obfuscate the data. Okay. Here set obfuscate date true. We have set seeds in order to fix the seed. Here set days for the how to displace the dates. Okay, here plus 10 days. Okay, so this is the obfuscation pipeline. So here we apply, after applying the obfuscation on this free text. So as you can see here, we have patient name, Martin Chad, date of birth, 11 2000, and so on. And after the obfuscation, we have patient name Marian Galus. So Martin Chad is obfuscated into this name, Marian Galus, and date of birth. Since we configured the pipeline to obfuscate the date with plus 10 days, and original days was 1, so 1 plus 10, so it is 11. Okay, so this is the obfuscate value of the this date, and here as you can see we have a repetition of the same name, so which keeps the consistency on the same patient. Okay, so Martin Chad, it is obfuscated into Marian Galus, Marian Galus. Okay, here we have the age 24 obfuscated into 28 years old. Here we have structured data obfuscation for the same patient. So let's see. So here we have Martin Chat, okay, with the same date of birth, okay, and the output of the obfuscation. So it is the same Marian Galus. It is the same name used in the unstructured text. So Marian Galus, and then plus 10 days. So here we have 11, okay. So it is the same obfuscated date as we have here, okay, in the obfuscated unstructured text, and here in the structured text we have the same obfuscated values as well, as you can see here. Okay, for the PDF data obfuscation, again, we added some of the pre-processing, some of the visual NLP to extract information from the scanned PDF, and we feed, again here, we use obfuscate in the DICOM annotator, and with the same parameters to keep consistency, and here we built the final pipeline for the PDF. Here we transform our inputs PDF, so this is the, remember this is the inputs PDF, Martin Chat, this is 2000, and this is Martin Chat. Here we have 24 years old and Martin Chat, so on. So this is the input. Okay, so let's see the output from the PDF obfuscation. So this is output. So as you can see here, we have Marian Galus. It is the same obfuscated value that we have in the structured and unstructured free text. And here, as you can see here, so this is the obfuscated date, so 11. So as you can see here, it is the same obfuscated value that we have in the structured and unstructured. Again here, Marian Galus, okay, and 28. Remember, we had the same age obfuscated value. It was 20, 28, as you can see here, okay, and here we have the same age, obfuscated age. So remember, the input was 24, so it is obfuscated into 28 in the unstructured text, again in the structured text 28, and again in the PDF obfuscated or obfuscation, it is 28 again. Okay, and of course we keep also the consistency across the whole PHIs that we have, Marian Galus, and the same dates as well. So as you can see here, so the same dates and the same patient name obfuscated value. Let's see the DICOM data obfuscation. Again, so we add some visual NLP component at the beginning, and after that we put it all together into one pipeline with of course with healthcare NLP pipeline, and we just load our DICOM, the same DICOM. So here we have the inputs, okay, we have the metadata of the same patient, which is Martin Chad. This is the input, and as you can see here, we have the pixel image, so Martin Chad and the date. Okay, let's see the output from the obfuscated or the DICOM obfuscation pipeline. So here we fit the pipeline, we transform, and we got the results. So let's see the results. Here we have the image. So let's see. Yeah, so as you can see here, so let me zoom in a little bit if I can, just to show you. So as you can see here, so the Martin chart is obfuscated into Marian Galus, which is the same value as we had in the structured, unstructured, and also in the PDF. Okay, so it is martingale and also the same obfuscated date as well. So let's see the obfuscated metadata values. Okay, so here we have some of the components that we use in order to obfuscate also the metadata of the DICOM image. So let's see directly the results. So this is the metadata output. So let's see the patient name. So this is the patient name. So the value is Marian Galius. So it is well obfuscated. And here we have the dates. Okay, some of the dates that are well obfuscated as well, and by keeping consistency for the same patient. Okay. Uh, I think that's all regarding the demo. So we have two notebooks, one for multimodal masking and the second one for multimodal obfuscation for the same patient, in which we have multiple modalities, multiple document types, and we keep consistency while obfuscating. Also, we mask the wall PHIs, and it is fully flexible. You can play with the pipeline. You can build your custom pipeline using Johnson Labs capabilities. So let me come back here to the presentation just to show you some of the important links and resources. So here we have the models hub, in which you can find a lot of pretend pipelines, a lot of pretend models that you can use to build your pipeline. Here we have we do have Spark NLP workshop, Visual NLP workshop, in which you can see a lot of runnable notebooks to play with Johnson Labs capabilities. And also here we have the JSL NLP documentation, some of the demos if you want to see them, some of the live demos, and also we do have JSL Learning Hub. And now, of course, we have some of the other important things regarding Databricks Trust Center. We have Databricks Compliance Center, and we have Databricks Security Best Practices. So I invite you to see and those links for more details regarding the documentation, how to use Databricks, how to use Johnson Labs capabilities, libraries, and so on. Okay, I guess that's all. No, thank you, and we can move to the questions.